Hey everyone, in this video we're going to solve the original problem we started the series out with. So that was classifying a mystery flower based on its measurements only. Okay, so in that problem, this is what the data looked like. She had measurements for each flower, the length and width of its petal, and then the type of flower. She used a number to represent the type, so 1 was red and 0 was blue. So each of the rows of this table represents a flower, but she forgot to write down the type of the last one. So she wants to make a neural network that takes in the two measurements, the length and width of each flower, and predict the type. So this is a visual representation of that network, and here is a mathematical representation. She's really going to weight the length of the flower by one parameter of the network, and that's this edge here, and she's going to weight the width, another feature of the flower, by another parameter, W2, and then she's going to add a bias to it, and we'll see why that's useful in a second. And then she's going to wrap everything in a sigmoid, and that just squishes the values to be between 0 and 1, because the type that she's trying to predict only has values between 0 and 1. And she can consider the output of this network. If it's above 0.5, she can consider that a 1, or like the network is trying to tell her, it's a red flower. And if it's below 0.5, she can consider that to be a blue flower. So if we take a look at what the network can actually represent, I'm going to graph it, and I'm going to use the x and the z axes to represent the features of our flower, and this plane here, really each point is the network evaluated for those specific features. So if we look at straight down, this is x equals 1, z equals 1. So I feed 1, 1 into the network and get out a specific value, and that becomes the y coordinate of the point. So now I can play around with the parameters w1, w2, and b, and we can see what they do. So if I change w1, you can see how the surface changes like this. And if we think about it for a second, really, you can see that if I go straight on like this, w1 is modifying or weighting the length feature, and I'm using the x-axis to represent the length feature down here in this surface plot. So if I give it a positive slope, the plane is sloping upwards like this. As x increases, you know, the output increases, and then the sigmoid just squashes that value. So if I give it a negative slope, you can see how as x increases, the output of the network decreases. And a 0 slope, well, sigmoid of 0 is 0.5, so the network's output is 0.5 for all these values, because it's basically w1 is 0, w2 is 0, and b is 0, so we have sigmoid of 0 everywhere on this plane. Now the same is true if I look at this plot with z here. Now w2 is weighting z, so if I give it a positive slope, it slopes up, negative slope, it slopes down. And finally b is kind of like this global change that you can apply to the network's output. It affects the global output of the network since it's not weighting any feature. So if I increase b, I can increase the network's output up to close to 1, and if I decrease it, I can decrease the network's output close to 0. So you can see how that works. Now what's cool is when we have values for w1, w2, and b. So let's give w1 something and then w2 something. If we have them both be positive, you can see we get this shape, where for positive values of x and z, or our two features, length and width, the network's output is positive. And now you can see what b does. You see how this is kind of always centered about the origin here, the change in the network's output. Like no matter what I do with the two W's, it's always centered right at the origin. But luckily, with B, we can basically shift that line, that change in the network, forwards or backwards. What we're really doing is shifting the entire plane up, and that makes more of this side get squished into 1. And if we shift it down, more of this side is getting squished into 0, and then we have the bit of the plane that goes above 1 getting squished into 1. So with the bias, we get a lot more expressiveness in the network. And so just for fun, I took the sigmoid off of our network, and you can see that W1 affects the slope of the plane in the x-axis, and W2 affects the slope of the plane in the z-axis, and then the bias shifts the plane up and down. So that's what our parameters are doing, but when you wrap it in a sigmoid, you wrap this weighted sum in a sigmoid, you get that surface that we saw earlier. Okay, so now I've added our data. So for each flower, I moved over to the right by its length and then up by its width and plopped a point down. And for its type, if it's a blue flower, I made its y-coordinate 0. And if it's a red flower, I made its y-coordinate 1. And I also color-coded them. Now, the mystery flower here is in orange. So, we can see that for different features, we want our network's output to match the y-coordinates of these points. And right now it's kind of in the middle. So let's change our parameters by hand and see if we can get it to kind of match these points. We want the network's output to be low for these blue points and high for these red points. So I think we're going to need 2 positive weights. So we'll make W1 positive, W2 positive. And then we can shift this back and forth with B. And let's take a look here. It's going to be kind of hard to tell. Oops, it looks like we need to move a lot more over here with B. And the larger our weights are, the stronger the slope of our function is going to be, our neural network. That's looking okay. Let's see, it's kind of difficult to separate these points because they're so close right here. It's going to need such a strong slope, an exact slope. But we could push it even further. My plane is losing resolution now. That's okay. Let's see how that looks. That looks okay. It's just this blue point here, so we need to shift the plane further. So you can see, it's not exact, but you can see how it's like the surface is trying to come up to meet these points. We want the network's output to be 1 for these feature values, and we want the network's output to be 0 for these feature values of the blue flowers. And you can also see that the orange, our mystery flower, is, if we fed it into the network, let's actually do that. Okay, so we feed this mystery flower's coordinates into the neural network and get out a y-coordinate. You can see that it's up there now with all the other red flowers. So that's a good indication that it's probably a red flower too. So let's see, just to prove that that's being fed through. Yeah, So you can see how as I change the weights, it changes the output of the network for that point. So that's kind of what you would do when you're trying to predict what this flower is. You feed its coordinates in and see what the output is. And since the output is a 1 or close to a 1, you can predict that it's a red flower. Now let's see how to train this network automatically instead of playing with the parameters by hand. Okay, here's how we solve the problem with JavaScript. I want to thank Alex for leaving this awesome comment on my channel where he solved the problem using JavaScript and kind of started me off on solving it with JavaScript as well by modifying from his code. So thanks Alex for that. That was really cool to see you take the initiative, to go and try and solve the problem yourself. But anyways, this is how I ended up solving it. For every grid point in this coordinate system, I color it based on the output of the network at that point. So you can see in the upper left-hand corner here, my mouse is currently at, let's say, 0.11, and you can see the prediction is 0. Up in the upper left-hand corner, it says prediction 0. And as I move my mouse, you can see the prediction increases until we're over here, and let's say I'm over here at this point of 5.5 and about 1, and the network's prediction is 1 over here, or very close to 1. It'll never be more than 1. So I color all these grid points red if they're above 0.5, and I color them blue if they're below 0.5, and you can see that the network has found a solution where it's split, the two types of flowers based off of their length and width. And you can also see the mystery flower over here, and it's likely a good bet to think it's red, right? The network's output is red for these coordinates, for these features of this mystery flower. Now, every time you refresh this page, the network tries to solve the problem. And you can see the randomness, right? Because we start the weights off with random values, and we pick random points to come to a solution. Now I'm just going to walk you through the JavaScript code pretty quickly. So let's take a look at that. So we start off with our training data, and that's a bunch of variables. Each one of these lines of code is one flower, and you can see the first feature is the length of the flower, the second feature is the width, and then I put the type here as a number, right? So these are all blue flowers, data blue 1, data blue 2, data blue 3, data blue 4. So they all have a 0 here for their type. Now for the 4 red flowers, I do the same thing. So this flower has a length of 3, a width of 1.5, and a type of red or 1. So that's our data. Then we have our unknown data point, which has a length of 4.5 and a width of 1, and something like we don't know what it should be, but we can make a guess that it should be 1 visually looking at it with all the other points. Now I take all these flowers and just put them in a whole new list so I have easy access to them. I define sigmoid, which we're going to use, and if you remember, that's 1 over 1 plus e to the negative x. Now here's how we train it. Here's how we solve it. So we have 3 parameters, w1, w2, and b, and I start them off as random numbers, and we'll see more about weight initialization in future videos. Now I pick a learning rate, and remember this is just the fraction of the update that we're going to be using to update these parameters. So we get random parameters, pick a learning rate, and now we do some iterations. This is our big training loop. So we do 50,000 iterations for this problem, which may seem like a lot. It probably is. We could make the learning rate larger, but I like to use a smaller learning rate and lots of iterations to get a nice solution. Now here's how we train our network. We pick a random point, a random flower. So now we're looking at a single flower. I get out its target. I get out its type, which becomes our target. So this will be a 0. This target variable will be a 0 for blue flowers and 1 for red flowers. Now we do the feed forward part of our neural network. So we weight the first feature by W1, and we weight the second feature by W2, and then we add B. So we basically add up these three things, and then we take sigmoid of that. And that is our network's prediction. So I just call that pred. And we want to bring the prediction close to the target. So that's why we're using the squared error cost function. Now we need to take the partial of this cost with respect to all of the parameters. And so that's a bit complicated, but all we do is use the chain rule. And so we're going to take the partial of the cost with respect to just this pred variable first, and that's going to be the power rule. So we bring the 2 out front and decrement the exponent. So this is the derivative of the cost with respect to the prediction right here, this variable. Now we have to take the derivative of the prediction with respect to this z variable. And if you remember, the prediction is sigmoid of z, so really we have to take the derivative of sigmoid. It turns out that the derivative of sigmoid is actually sigmoid times 1 minus sigmoid. So this is the derivative of sigmoid. And now, you know, we're bringing how this cost function changes through each of the functions. It's like it's a nested set of functions. So we're bringing how it's changing through each function. So we brought how it changed through this power, and we brought how it changed through the sigmoid, and now we're at the z part. And now we want to know, how does z change when W1 changes? And that's this variable here. How does z change when W1 changes? Well, it changes by whatever point 0 is. Because you can see, if we thought of the slope of this just concerning W1, we can forget about all this stuff out here, and we can see that for a small change in W1, we're going to get a small amount of point 0. So the way that z changes with W1 is by point 0, or the first feature of our flower, you know, point indexing in here, 0 is the first feature of our flower. Then we want to know how z changes when W2 changes, and that's the same argument. We can forget about everything else and just look at what is multiplying W2, and that's 0.1, or the second feature of the flower. So how does z change with W2? Well, it changes by 0.1. And finally, how does z change when B changes? Well, it just changes by 1. You know, what is the partial of z with respect to B? And you can see B, it's really B times 1 here, so the partial is 1. So now we're all set up to find how does the cost change when each of our parameters change. And here's how we do it. We use the chain rule, so we say, well, how does the cost change when W1 changes? Well, we need to know, how does the cost change when our prediction changes, times how much the prediction changes when z changes, times how much z changes when W1 changes. So if I'm losing you here, don't worry. There's a lot of libraries, machine learning libraries, that does this stuff for you too. But basically, we're trying to figure out, how does the cost change when each of our parameters change? And that will tell us how to change our parameters then. So we do the same thing for W2. We say, how does the cost change when W2 changes? Well, that's how the cost changes when the prediction changes, times how the prediction changes when z changes, times how z changes when W2 changes. And now we do the same thing for B. You know, how does the cost change when B changes? Well, it's going to change by how the cost changes when the prediction changes, times how the prediction changes when z changes, times how z changes when B changes. So these are our updates. Now here's a different way to look at taking the partial derivative. So we have our cost here, and I've given intermediate calculations a name. So our cost is the difference squared. The difference is the prediction minus the target. The prediction, you remember, is sigmoid of this weighted sum, which I call z. And z is the weighted sum here, W1 times length plus W2 times width plus B. Now I can represent the cost visually as well in this tree diagram. So values kind of flow upward, and go through these little computation nodes. So W1 and length are fed into this multiply, and you can see that over here as well. W2 and width are fed into a multiply, and here they are. And then B and 1 are fed into a multiply, and you can see that here. We just don't have the 1 over here. And I do this for reasons you'll see later. You know, why would I multiply B by 1 if it's just B? But it'll make things more clear when we take the partial derivative. So then the output of these multiplications all go into a sum. And you can see that here. It's like this is the first multiplication plus the second plus the third. So those all go into this sum. And then we call the value of that sum z. And that's the same as over here. Then we take whatever z is and feed it through sigmoid. And you can see here we're feeding z through sigmoid. And we call whatever that is pred, short for prediction. Now we take the difference of the prediction and the target, you can see right here, and that's the same as the prediction plus minus 1 times the target. So again, I do it this way for when we take the partial derivative. It'll make things a bit easier. And we call the value at this plus diff. You can see that right here, diff. And then we square diff right here, squaring it, and we call that value cost. So now we're ready to take the partial derivative of cost with respect to any of our parameters, W1, W2, or B. And all that means, again, is how is the cost going to change for a small change in, let's say, W1. So let's focus in on W1. And to figure out how the cost is going to change when W1 changes, we need to figure out some intermediate results before we can work our way all the way back to W1. So first, we could ask ourselves, well, how is the cost going to change when the difference changes, when this prediction minus target changes? And we can see, well, the cost is equal to the difference squared. And knowing the power rule, we know to take the derivative of something squared, we bring the exponent out in front and decrement it, and we get 2 times whatever was in the square. So I'm going to write over here 2 times diff. So that's how the cost changes when the difference changes. And now we need to know, how does the difference change when the prediction changes? So we're working our way back. How do these intermediate results change when stuff that they depend upon change? Now we want to know how diff changes when stuff that depends on W1 change. So pred depends on W1. So we're going to take the derivative of diff with respect to pred, and we have to bring that through this sum. Whenever you see a sum or a difference, you remember the derivative of a sum is the sum of derivatives. So what that means is we're going to take the derivative of each side, the derivative of pred with respect to pred, the derivative of this multiplication with respect to pred, and we're going to add them. So the derivative of pred with respect to itself is 1 plus the derivative of this multiplication with respect to pred, which is 0. And so we just get 1 plus 0, or 1. Now we need to know, how does the prediction change when z changes? And you can see that the prediction is just sigmoid of z. So we have to know, well, how do we bring the derivative through sigmoid? And that is just the derivative of sigmoid evaluated at z. And the derivative of sigmoid I write as sigmoid prime. That's the same thing. And remember, this is the slope of sigmoid at a specific z value. So you can also remember that the derivative of sigmoid is sigmoid times 1 minus sigmoid. And that's what we use in the code before. But I'm just writing this shortly as sigmoid prime. Now, we can bring the derivative all the way back to z. And here's where we're going to figure out how z is changing when one of our parameters change, right? So we have to bring the derivative through this plus, and you can think of these multiplications as their own variables, like this is m1, and here it is here. So we're saying the derivative of z with respect to m1, and remember, the derivative of anything with respect to itself is 1, so that's where we get this 1. And now we can bring it through this multiplication. We're like working our way through this graph all the way to stuff that's touching W1. So the derivative of multiplication with respect to one of its operands is always the other operand. So in this case, the derivative of this multiplication with respect to W1 is going to be length. And that's it. We've taken the partial derivative of the cost with respect to W1. All we have to do is multiply everything you see in red here, and we'll have worked our way back all the way to W1. And that resulting thing is just going to be a number, and that will tell us how the cost is going to change for a very tiny change in W1. Now what's cool about this graph way of thinking is if we want to take a different partial of the cost, let's say with respect to this parameter W2, we can reuse all this calculation up here up until the point that the graph branches off and we need to be, concerning ourselves with these elements. So the only thing we have to change is this final link in the chain here. So we're concerning ourselves with this multiplication now, and again the derivative of a multiplication with respect to one of its operands is always the other operand, right? The operands of this one are W2 and width, and so it's with respect to W2, so it's the other operand, so it's width. And finally, if we want the partial of cost with respect to B, all we have to do again is change this final element, and it's just a 1 this time. So this partial is really simple. It's just 2 times difference times 1 times sigmoid prime of z times 1 times 1. So that's how we find our 3 partials of the cost with respect to each parameter. It may be a bit confusing at first. I know I was definitely confused. It took me multiple weeks, maybe even a month or two, before it made any sense to me at all. So let me know in the comments if this graphical way of taking these partial derivatives makes sense. And again, I just want to remind you, you don't have to do this when you're actually using this stuff. A lot of libraries have built-in automatic differentiation, so you don't have to concern yourself with this stuff because a lot of errors can be introduced as you're trying to find these partial derivatives. Now, these are the way we can change our parameters to increase the cost the most, but we want to decrease the cost, so we subtract them from our parameters, and also we subtract only a small fraction of them. We multiply them by the learning rate so that we don't overstep our minimum. Now this training function returns the learned parameters here in a dictionary. So I can run this. It'll start with random weights, iterate through by picking random flowers, improving the network's prediction per flower over and over and over 50,000 times, and then return the learned parameters. And then the rest of this code is just to visualize the output on this graph like this. So we'll see how to solve this problem with automatic differentiation in my general series on neural networks, where we're going to scale things up. We're going to have more parameters, multiple layers, see what's going on at each layer, different architectures, different network architectures. So stick around for that. I'm going to also do some investigative kind of pieces on like Siri or Google Voice, how do these modern applications of machine learning work, and maybe some robotics stuff. We'll get back into, if you've seen my creature things, we could look at how those work. Let me know in the comments what you want me to cover next or what I failed to cover in this series, and I'll make a few videos on that. But other than that, I just want to say thanks, and I'll see you in the next video.